x and y are two independent IID uniform 0, 1. I hope both of you are aware of what this means. I hope both of you are aware of this.
Yes.
So if x and y are two independent random variables and they follow the same distribution, uniform 0, 1, then we have to find the probability that x times y is greater than a w, let's say. In other words, it's you have to find out kind of the CDF, the cumulative distribution function of this random variable x times y. Now this may seem quite easy in the sense that okay, x and y are IID, but since this sample space, since the support is restricted, like it's 0, 1, you will see that we will run into a geometric issue. And that is exactly the problem I'm going to discuss with you. Okay, so you have to find the probability x times y is greater than w. Okay, so how to approach this problem? The way to approach this problem, there are different multiple ways to approach this problem. Let me write down it. Write down, x, y follows IID uniform. Right? We have to find out. Oh, there are two people who want to join. So we have to find out probability x times y greater than some w, some constant w. Okay. So how to approach this problem? So there are two ways to approach this problem. One is a geometric way, and one is a purely algebraic way. And my goal is to make you understand that how the geometric way and the algebraic way come together. What is the relationship? So let's try out the basic approach, the simple geometric problem first. So when we say x and y are uniform 0, 1, we can easily draw this diagram. So this is x, this is y. So x is the random variable x and y is the random variable y, and it is x is taking values between 0 and 1. Similarly, y is taking values between 0 and 1. So we get this square. So this square is nothing but the support. So this, when we say x, y, it's essentially x times y, x cross product of y. The support x, y. So this is the distribution. So x, y is distributed about this support. This is the support. This is the support. So support is the region in the sample space where the random variable has positive probability, or if it's a continuous random variable, it has positive density, like probability density function, positive values only. So this is the support of x, y. So we will try to see that when we say x times y greater than w, what, like this region, what does this region represent in the support? Now, what is the distributed density of x, y? Since they're IID uniform, this is the support, but if you imagine in z dimension, you will see that essentially it's 1 all over this. So the total volume will become 1 if you integrate it, and hence it's a valid probability density function of this joint distribution. So this is a support, and what we will do is then, as I said, we will draw this region x, y, x times y is greater than w. So what does this region, like, which is the region here? If you think carefully, so you can say that in some sense y is greater than w by x. This is a region here, and this is nothing but a hyperbola. If you recapitulate your ideas from high school math, so this will become a hyperbola. Okay, so let's draw an approximate hyperbola like this. This will become a hyperbola. All good till this point of time, guys? Akshat, Rohit, and Kartavya. Akshat and Rohit.
Yes.
So this becomes a
I have
hyperbola.
a question though.
Yes.
So because x and y are IID, they would also be symmetric, right?
So what do you mean by symmetric? Here, like symmetric random variables?
So yes.
Yes, yes. The idea it's symmetric, but here it will not be a symmetric thing because you can see the asymmetry here, x and y. So yeah, it's symmetric, but that will not help here in that sense.
Okay. So
But
the way you said y is greater than w over x, so we could also say x is greater than w
yeah,
over y.
yeah, exactly, exactly. We can also say that, but that will not help in our computation.
No, but I just it was a general question. So
Go
when
ahead.
we have two random variables that are IID with the
Yeah.
same distribution, we could hold one of them constant without the loss of generality, right? Or we can't
I
do
mean,
that.
no. I mean, there is no both are random variables, so we cannot do that constant. But what you're saying that will be the second part of the discussion, the algebraic aspect,
Okay,
how we can hold it
okay.
constant. So, so we have the issue is that the reason I want to teach you guys the reason is that we have all these algebraic ideas in our mind. Okay, like we can, for example, when you do a partial derivative, you can take one constant and take the derivative with the other respect to the other variable, right? But why do we do that? So we have this algebraic ideas that you have said similar just right now, but why is that true? What is happening underneath? What is the meaning of that? So that's one of my motivation to also do this talk. So, so this region is what we're interested in, and if you observe, this is nothing but this region, this area under this curve. Remember that this entire, like, it could have gone farther away, it's infinite, but since the support of x comma y is in this box, we get this. Okay, and one way is that we do the calculate the complement of the region. So this we calculate this. So let me show it here or maybe here. So we have this. We want to. So this is. So we want to calculate the area of this. We'll calculate the complement of that because that's easier to find out. So how to find the area under this curve? It's very simple. You see that here it takes a break. So here it breaks the symmetry of the curve. So we'll divide the region into this, and you can see this line is nothing but y is equal to w by x. So the place where it hits, the x place where it hits, here it's y is equal to 1. So this x will be here w. So this is w, and we will integrate it first. So integration of 0 to w by x dx plus, I hope you can see, plus, yeah, you can see, right, guys?
Yes.
Plus integration w to 1. Sorry, this will not be w by, this will be 1, right? The height is 1. This is 1. This will be 1. Plus here w by x dx. Okay. So this will be the area, and you can calculate it. It will come out to be log and something. This will be w, and this will probably come out w log w. Okay, if I'm not wrong, yes. So, or maybe I may be wrong, but this is an integration that we all know how to compute. And this is the solution, but the solution is we have found out probability xy less than equal to w. Now we will do 1 minus this to get probability xy greater than w. Okay, so this is the geometric solution. Did you understand, all of you guys? Akshat, Rohit, and Fang. Any questions?
Yeah.
It's simple. So remember this, that there is a break over here. Okay, now I will show you the algebraic method. And this algebraic method is where things get confusing a bit. And that's why you have to be a little bit careful when you're doing conditional probability. So in the algebraic method, we will just dash it out in the sense that we will write the probability expression. So we want to find out probability xy greater than w. Okay. Now, how to do it? When there are two random variables, how to do this? And you clearly understand that I mean, it's easy to do here because x and y are not dependent to each other, but there is a dependency, we'll see. So when you do this, when there are two variables, what you do, as Akshat has initially said, that we keep one variable constant. But what is the mathematics of that? What do we call that? That is called the law of total probability. Now, I will briefly revise what is law of total probability. It's very simple. It says that, so for probability, tree diagrams are extremely important. It cannot be compromised because that tree diagram can be generalized to continuous cases. So let's say x takes two cases. Okay, let's say A and B, and then there is a further case, let's say C. So this is A and this is C given A, and this is C given B. So probability of C can be written as nothing but probability of A intersection C plus B intersection C, because only two possibilities can happen. And so these are events. So this can be written as probability of C given A times probability of A plus probability of C given B times probability of B. Okay, so this is called law of total probability. If you generalize this to like finite number of cases, you will get, let's say, n events, then you will get I from 1 to n probability of C given AI into probability of AI. So what this means is that if you can do a task, let's say this task C, in AI different ways, sorry, n different ways, A1, A2, A3, and then there's a first to do the event A1, and then you do the rest of the event. Like when I say event, I am meaning task. So first, therefore, we have probability of AI, and then we multiply it with probability of the C given AI. The next step of C going to the C via AI. So this is the basic idea of law of total probability. Okay, so this is called law of total probability here. Why it's called? So this part, this multiplication part is called chain rule, and this addition part is the basic disjoint. Is like the addition principle of probability. So we get this to get law of total probability. Now, when you generalize this to continuous cases, it becomes integration. Okay, whatever is the support, probability of, let's say, x given y is equal to small y times the probability that the y, what is the probability of the y random variable taking values around y. So in the previous video, I explained that we are interested in the probability of y taking the values around small y. So that is nothing but the PDF times dy. So this is the probability. Okay, together. So the PDF doesn't make any sense. The PDF times dy, I have explained in the previous video, is nothing but the area of the probability of taking the random variable taking values in that small region. Okay. So this is the law of total probability where whatever the sample, the support is dy. Yeah. So this is the, as if you remember, this is the conditional part and this is the probability of y's in some sense. Does it make sense, all of you? Any questions? Akshat, Rohit and Fang?
No.
I do have a question.
Yeah, go ahead. Questions
So,
are important.
the PDF part says for the tiny delta y was the area under that curve, right? We are trying to find the probability around that
Okay, let me
small
explain.
y.
So here is a PDF. Okay. You have y and you take y plus dy. So this area under the curve can be approximated by, it's a kind of an approximate rectangle whose height is f of y, the PDF value, times the breadth, which is the distance between y and y plus dy, that is dy, small dy. So this area can be approximated by f y, so this one. Does it make sense?
Okay. So you multiplying the PDFs and the conditional probability gives you for a tiny for this conditional probability, a tiny change in y gives you the probability that we want.
Yeah, so conditional prob, okay, so think about this in this sense that when you have multiple random variables, the random variables are intricately related to each other. Okay.
Okay.
In this case, it's not, and you will see that. But it's like because all these random variables are inspired by a real world, right? And this real world, there's a temporal component to that. Naturally, the temporal component leads to this dependence, right, Akshat? So this is
Yes.
the way to think about it, the mental model. That think in temporal terms. When you're going to do a task, the task first can be divided into n steps. Okay. And each of those, then the final task is dependent on the previous n steps or events. So in this case, in this infinite case, imagine that there are infinitely many such paths. Okay. So the summation is going to infinity. Integration. That's why.
Yes.
So we
Okay.
have
Makes a
y
lot of
taking
sense.
all the values from 0 to 1, and for each of those values, it has a probability of taking values around that region, each of those values.
Okay.
So x given y is equal to y is the second probability, and f of y dy is nothing but the probability of that around taking values around that region of y value. Does it make sense?
Okay. Yeah.
This is nothing but the extension, the continuous extension of the discrete aspect. All good, Akshat?
Yes.
Good. Oh, why did I drop it? Anyways. So we can write this as integration. Integration over what? That's one important question. So usually people write, okay, 0, 1. We will say it's not true. So probability of y greater than small by w by x. By x is random variable, we have to condition over x. Condition over x. So we do given x is equal to small x. So just when we did given here, this capital X becomes small x, which we are saying doing constant. And now we are taking the probability of x taking values around small x. So this is the dx, fx dx part. And this is the conditional part. Does it make sense? All good?
Yes. All good.
Yeah. Very good. So now let's compute this. So this is very easy because this x is uniform. This becomes 1. So this becomes just dx. Now what about this? This is where we will use the independence. If x and y were not independent, then it would have been different. If let's say y is equal to x square, then we couldn't have done this. Okay. I mean something else. But here, since it's independent, probability of a given b is equal to probability of a. So this dependence on y, x goes away. So we get this times dx. Okay, now it's simple, but there's a catch. We forgot about the limit. Now, how do you understand? So this is what the issue with algebra. Okay, because you don't think in terms of the geometry. Imagine like we could have done this geometry problem in 2 dimensions, right? But what if there are n dimensions? So there's always an important aspect of computation of conditional probability to check the range or the support where x, and you will understand why. This is very dangerous. Okay, I have made this mistake multiple number of times, not in this problem but before. So this is very important, guys, because we do not tend to think about in terms of space. Okay, we only just do the computation. So it's very important thinking where is the support, what is the range of the random variable. Now how do you understand this? A good way is to put the values of x. So if you take x is equal to 0, okay, if you take x is equal to 0, you will see this value goes to infinity. If you take x is equal to 0, this value goes to infinity, and y is between 0 and 1. So it cannot take infinity. So therefore, there must be a lower bound, an upper bound on x. Make sense? Yeah, so you have a lower bound on x. because x cannot become very small. There must be a lower bound of x, because as you see, x goes to 0, this goes to infinity, and y cannot take values greater than infinity. So how to find this? It's very easy. So since you know that y is less than equal to 1, y is less than equal to 1, so you just apply this. Okay. And you can easily see, remove the y. So you get w by x less than equal to 1. So you get x greater than equal to w. So we replace this by w. Okay. And this is exactly the same thing we have done in the other case. In the other case, we did less than equal to w by x, right? We want to see the below area, and if you do less than equal to w, you will see that we have to divide the area in 2 halves. So what I'm saying is that this restriction is equivalent. If you remember, the restriction is equivalent to dividing this area, this x region, into 2 halves. 0 to w and w to 1. Does it make sense, all of you? To divide that region into 2 halves, 0 to x and w to 1. And that's exactly, it's coming out algebraically here also. But it was not intuitive enough. Because how did we give this limit? Because we know that it's on x, dx, and x can take values between 0 and 1, right? But there is a dependence, space dependence. So, and it's intuitive more, you are more prone to do this because you're given x and y are independent. So you will think that, okay, x and y are independent, so the limit will be 0 to 1. But no, the space is limited here. So that's where the dependence also comes in, the restriction of the space also comes in. No dependence is there, but restriction of the space comes in. And that's why it's very important to check this range. This is the lesson I want to teach you by this today's class, is this, that always while doing conditional probability or any kind of probability problems, look at the range, because of the restriction of restriction of the values it can take, the support, or the conditional or the dependence on one variable over another can cause an issue. Okay, so this is very important, and it's very easy to miss, specifically in simple problems like this. Even in simple problems like this, you can miss this. So now you can easily calculate it. It's the same. Like now this is y is random variable, so it's w to 1. This is nothing but it's a uniform random variable, so it's only 1 minus w by x. So it's taking values just above w, so it's 1 minus w by x dx, and then you can see it's the same calculation. Okay, you can do 1 minus w minus log the something like this, it will come out to be. But the lesson of today's class is this, that instead of 0 to 1, it has to become w. The dependence, the restriction of the space plays a very important, like gives us a very important lesson here. Okay, I hope you enjoyed it, and let me know if you have any further questions. I hope you understood it, whatever I have said. Okay. Thank you guys for joining. Thank you, Rohit. Thank you, Akshay. Yes, go ahead.
So basically, even if we have a random variable x or y,
Yes.
the range or the support is dependent on the random variable, not the other way around.
No. A random variable has the support. Each random variable has a support, right?
Yeah.
So when you're computing the integrations, essentially, okay, so what we are doing? Probability is nothing but the kind of the measure of the space. Okay.
Measure of it. Yeah.
Right. Now the measure of the space can be, you can just, let's say there is a length. Okay. So there is this length, or let's say the length of my finger. It is a measure. But I can also define a height over here, which tells you, let's say, how much is the thickness of my finger here. Okay, because my finger is not uniform. So along this length, I can define that height, and that will and make it relative to the entire thing, so that the integration becomes 1. So that will kind of define another kind of definition of the region, and that is exactly what PDF does. PDF essentially is a distribution of the space, like, or giving different importance to different regions. uniform distribution gives the same importance, but a probability density function kind of gives different importance of different regions in space, even in the length of my finger. So it gives a different different measure of this, or different measure of my finger, right? So what I'm saying is that essentially it's kind of the measure of the space we are looking at, okay, in some sense. So we have to investigate the space very carefully. For example, if we had y is equal to x square, then the space will be very different, right? Then the space will be a single line. Even if we have y is equal to x square, the space will be a single line, if you can imagine. For every x value, x square is taking a different value. Do you see what I'm saying?
Yeah.
So the basic idea is that we are kind of probabilities measuring the space where the random variable lies. Okay. Probability is about measuring the space we are lying in that problem. And that space changes. That space has restrictions from problem to problem. And it's always a good idea to verify the restricted space area. It's always a good idea to understand the geometry of the space, even algebraically. So, yeah. So does it answer your question, Akshar? I have a habit of elongating the answer.
No. The longer the better, because yeah, it makes sense. Yeah.
Any other question? So Fang asked that what would be our approach if x and y are not given to be independent? No, absolutely. Please ask this question. See, if x and y are not given to be independent, here the dependence of here x is equal to x would have been taken into account, and then whatever there, and then this would change. Okay, this would change. Or there can be multiple ways of defining dependence. The way to define dependence is to define a joint random variable. So when it's independent, the joint random variable is multiplication of the y's PDF, and the joint random variable's PDF is the multiplication of, let me write it down. So when it's not dependent, it's dependent, then we write like the joint random variables this of the two random variables x, y is multiplication of this individual random variables PDF. Okay. So, but when they're dependent, this will be not multiplication. This will be something else. Okay. So that we have to define first. So this result that we have written here, that integration, let's say whatever the support is, probability of xy greater than w. Okay. So here there are multiple ways of doing it. Here you can do it over dx. So here we have to do fx dx. So here you have joint random variable. Okay. So x comma y. It will be two integrations. Let's say over x over y. So this you will know, right? And based on this, yeah. And actually from here you will get to know. Actually from here you will get to, I think the best way is to do like this. You will get to know this. The best way is to find this. Actually it depends upon the algebraic expression. But the best way is you have to find the conditions. From the joint distribution, you can find everything. So from the joint distribution f of x comma y, you can find f of y given x. You can find f of x, you can find f of y. How can you find f of y? You do integration over x. How do you find f of x? You do integration over y. How do you find f of y given x? Y given x is nothing but the joint distribution divided by f of x, right? So you first find f of x and f of y, and then you can find the individual conditional distribution. So once you find the conditional distribution, this becomes y greater than this, given this. So now this is, you find the probability using y given x distribution here. Okay, you find the probability given of y given x distribution. You already know the algebraic expression. Use the algebraic expression to find out this probability. And you already know the marginal x, and then you multiply. So the first will be over dy here. This will be dy. Here it was easy. but here it will be, this first integration will be over dy, the second integration will be over dx. Now, if x was dependent on y, it depends on how they're related. If how the algebraically they are related. If x given y was more computable in nature, then you do x given y, and then that will be f of y, f of like this density of y. Does it make sense? Fine. So, for example, seems very much like expectation. I think I mean, expectation. Of course, every probability is a expectation of integer random variable, right? So, I think you find a lot of every expectation is a probability. Sorry, every expectation has a probability. No. Sorry. No. Every probability is an expectation. Sorry. So, and all of them includes integration. And integration is nothing but a way of measuring the space area. Here, if it was expectation, it will be x times that. So everything will seem connected because it's an integration, and that's the connection point. And that's why later on, measure theory becomes very useful if you want to do a quant finance, like you want to understand measure theory. So measure theory is where it comes up to be useful, because not all spaces can be integrated like this. Like if you take the space, so I'm going to very different directions. Thanks for the question. But yeah, so all space cannot be measured like using integration, because this integration is a very specific definition of using Riemannian sum having an upper. So how is integration defined? Riemann integration. It defines like, it's the same. We define it like by this small, just like you remember the limit. So we define a smaller limit and we define an upper limit. And as this becomes smaller, now the divisions become more and more. This upper limit converges to the smaller limit, and if the limit converges, that value is called the integration. That's how the integration is defined, Riemann integration. Okay. But if you take this simple function, if x is equal to 1 if irrational and 0 if rational, then you cannot integrate this. Okay, because you will see the upper limit will become 1 and the lower limit will become 0. Because both rational and irrational are infinite, it kind of dense in the 0, 1 interval. So for every interval, you will find one rational number and one irrational number. So by the density property, you can always prove that the upper limit is 1 and the lower limit is 0. So the limit doesn't exist. So you cannot integrate here, right? But the idea is what? There are more irrationals than rationals. So ideally, the area should be 1. But still, it's not integrable. So the idea of area using integration, or idea of measure of the space using integration, has to be extended and generalized to a different measure. And that's why Lebesgue measure came in 1913. Lebesgue measure came in, where it defined the area. So there the area was defined in a different way. Okay, that's a different discussion altogether. But yeah, that area was defined very much in terms of x. It's very beautiful actually. So yeah, they different measure. In fact, this Lebesgue measure was introduced in 1913, using which Kolmogorov set the foundations of probability in 1933. Okay, so measure was a very big part of probability, because there are certain interesting spaces where you cannot give a measure. It's very hard to give a measure, and there are a lot of interesting spaces. So the whole theory was built because you cannot give measure to every kind of spaces. The measure theory and probability theory, if it seems too abstract, it's because mathematicians have to work hard. Otherwise, what will happen is that you will get 1 + 1 is equal to 5. Okay, this kind of things will happen, and you can read about that online. Okay, I think it's Banach-Tarski paradox. So you can read about how you can create multiple spheres by rotating, and it will turn out to be 1 is equal to 5, something like this. So essentially, the idea is that you cannot find the measure of any space. So when you can, there are certain examples, there need to be a very specific definition of measure. What is measure? And hence probability. Probability is just an example of measure. So probability is a language with its own framework. Yes, so probability is a language with its own framework, of course. Rather, you can think of it that probability is a measure of the space. This is the best way, okay, to think about it, that probability is the measure of a space. No, it's absolutely fine. It's a measure of a space. So intuitively, I mean, if you think that we say chance, and actually the whole idea of probability, why it's unintuitive, because we are tending to think of chance. So, but like, let's say today there is a 50% chance of rain or 80% chance of rain. That can be very, for example, the app we use here, when they say 80% chance of rain, they mean that in this district area, there is a chance of rain. There's 80% of this area which has chance of rain. Okay, that is one way of defining. In another, there's a temporal definition, let's say, or they have observed that this whole area, the entire area has at least one bit of rain 80% of the time out of the last 100 cases by statistical sense. So there are different ways. So essentially, it's measuring what do you mean by measure has to be specifically defined. Okay. So yeah. So it's very useful to think of probability as a measure of the space and think about it. So the idea of chance is nothing but the measure of the space. Okay. So I usually introduce probability like a fisherman. Like you have a big lake and you cast your net. So what is the chance of you getting fish? It depends upon how the measure of the net you are working with. So that's where the measure comes in. And it's a very interesting way of taking. Yeah. Any other questions? I hope it's useful to you guys. I hope it increases your intuition. Any other questions? Okay. Thank you for your time. And I will see you sometime soon. Thanks for joining in very promptly.
Great, bye.
Thank you so much.
Absolutely. So just a question. I hope there was no issue in the view of the board, right? You can see.
No. I didn't expand my screen, so I couldn't. I thought that it was cut in. So yeah,
Okay.
I was wrong in the beginning.
See if anyone is on
Thank
computer.
you very
please-
much.
Okay. Thank you. Yeah. Bye-bye.